So hello everyone. Our team, which is me, Yulia, and Jörn, are going to present Protostar. So why are we here? We are looking for builders or hackers who are interested in building for the long term, and they're not interested in short-term gains. And that's why we wanted to present for Antalpha, because the hackers that come here, they have a different mindset. They want to build something which lasts longer. And the second question you should ask is, why should we care? There are so many folding schemes out there. Why we want to implement right now? So even there have been so much research going on into folding schemes, there haven't been like a real world use case. Even right now, there is no, you cannot verify Nova's proof on Ethereum. You cannot, they are not actually being used in some project. And that is a big gap in that we see, that there is a lot of research, but there is not a lot of work done in the implementation side. So Protostar one of the most important features of Protostar is this compressed verifier. So the compressed verifier, what it does, it takes degree D check, takes n degree D checks, and then compresses it to only 1 degree D check. So we are taking multiple degree D checks, which are very expensive to compute, and we compress it to a single degree D check. And there are multiple strategies for that, and this is what I implemented in this pull request. So this is the compressed square roots of powers of beta. So if you read the paper, the verifier and the prover can send challenges, which is this beta parameter, and then we can batch them up in a single message. And that is one of the efficient things about Protostar. So as we said, even right now, after so much, Nova's implementation was released almost 1.5 years ago, and still there hasn't been any project or still you cannot verify Nova's proof on Ethereum, because the proof that you get is still very large. So for Ethereum, we both need a short proof and we also need a faster proof generation, and these two are very difficult to achieve. So one of the common strategies to have both a short proof with and in order to verify on Ethereum, we can aggregate these circuits. So most of the folding schemes, they are run on these cycles of curves, because you have to do some non-native operations. So because they're expensive, we use cycle of curves, and at the end, we aggregate those into a final circuit. And the advantage of this aggregation is that if it is done correctly, we can have like a very short proof, and we would be able to verify on Ethereum. So right now, the Protostar uses hyperplonk proving system on the backend, and so as we saw that there are these two cycles of curve. So one of these cycles is this Grumpkin curve, and this Grumpkin curve produces a secondary proof, which is using this Hyrax polynomial commitment scheme. And then the final aggregated proof, which takes in the secondary proof, is done on BN254 curve. And this is done using Gemini PCS. So if we want to verify the final aggregated proof on Ethereum, we would also have to verify this secondary proof, which is proved inside the final proof. And in order to verify this secondary proof, we have to do a lot of non-native operations, which is very costly. So if we were so for the snark verifier, we would have to verify this final proof, which is done on BN254 curve, and we would have to verify this Gemini PCS scheme. And Yulia will talk about it more. So what are the states of the proof right now? So right now, because we want to make the aggregation process more efficient, we we are testing the circuit with zero constraints, and there are 14 variables and 3 steps. So this is mostly done to find out what are the proof sizes of after the aggregation. So the secondary proof size comes out to be like 30 kilobytes, and this one is the non-pairing proof, and which is done on the Grumpkin curve, and it takes about 10 seconds. But the primary proof, which is the final proof output by the Protostar implementation, it is 10 kilobytes, which is which still can be verified with Ethereum, but it takes 2 minutes. So it takes a lot of time, and we need a more efficient implementation. So as I said, because for aggregation circuit, we have to do a lot of non-native operations, and Axiom's library is highly efficient at these for these operations. So what we tried to do was to port the aggregation circuit into the Axiom's library. So Axiom's library has this FP chip and an ECC chip. So FP chip is used to do all the non-native field operations, and these field operations are done for the sum check protocol in order to verify the secondary proof. And then we use the ECC chip, which is the elliptic curve chip, using to do these native curve operations. And most of these operations are like fixed MSM, variable MSM, and this is what is done on the secondary curve. So I'll go into the code based after Yulia is done with the Gemini chip. Yulia, do you want to introduce yourself and start? So yeah. Can you make her the host? Let's see.
Boom.
Eugene, can you make Yulia the host?
I think I can share tabs. I'm not sure.
You can share.
Uh,
他要干嘛呀？没有理解。
它那个优丽社团给
OK OK OK。
yeah, I think I'm all good.
Okay, then start sharing, or yeah, go ahead.
Is it working? Can you see my can you see my beautiful slides?
So I think wait, I will stop sharing. So
Yeah.
yeah.
Oh, it's OK。
Yes.
Let me try again. Can you see my slides now?
Yes.
Yes.
I wonder if we can make them full screen. No. I don't think so. Okay. Let's just make them very large then. Okay, I'm Yulia. I participated in this project. Thank you for the invitation to speak here. So I'm going to talk about one component of this project that was the Gemini chip. And the reason it's called Gemini is because it's very much inspired by a paper that's called Gemini by 4 authors. but specifically by a very, very small chunk of it that has some beautiful insight on how to commit to multilinear polynomials without ever touching any multivariable polynomials at all. And then there was introduced some optimization by Aztec, and they also they also pointed out that if you want to evaluate several polynomials at the same point, then you can come up with a random linear combination of them and evaluate them all together at the same point. Okay, so let's let me maybe explain what it's supposed to do. Let me first explain where it's in the protocol. I think I touched on that, but yes, the Gemini chip. It's not supposed to be one word, but it's supposed to deal with multilinear polynomials that come from the Hyperplonk component of the protocol and generate several KCG commitments instead of any multi-variable commitments. Right. Now I think I should explain how it works. This is pretty much from the paper. So let's say we have let's say the task that we have is that we have a polynomial that is linear, multilinear. It's linear in several variables, and we're going to in anticipation of what we're going to do, we're going to index the coefficients of the polynomial in this peculiar way. So we'll look at the powers of each variable, and we're going to treat those powers, they're 0 or 1. So we're going to treat them as bits of a number, and then from those bits we're going to compose the number, and that will be the index of the coefficient. All right, so this extremely creative notation pretty much suggests what we're going to do next. So we're going to take those coefficients AI, and we're going to treat them as coefficients of a single variable polynomial. So it's going to be a coefficient of the ith power of the variable. So what would be natural to do with a multivariable polynomial? Probably we would have to come up with some number of challenges, and then we'll be doing partial evaluation. So we're going to plug in almost all of the values of interest, and then one of the values will substitute by a random challenge, and then we'll do it several times. But just like I said, we just don't want to ever touch any multivariable commitments. So we come up with a completely different strategy instead. Like I already mentioned, we'll compose a single variable polynomials. Let me show again the polynomial in several variables that we had. So it looked like this. And now, if instead of the variables we put, well, instead of x0 we put x, instead of x1 we put x to the power 2, instead of x2 we put x to the power 4, etc. We'll get a polynomial in one variable, and that's exactly the polynomial that we'll be dealing with. Okay. So that's a polynomial. Now we're trying to do the multilinear evaluation. That's obviously not something that you can do with a single with a polynomial in one variable like this. So instead of trying to evaluate the polynomial, we'll fold it. So in the first step, we're going to compute a different single variate polynomial that will be composed from the part that only contains the even terms of the polynomial and the part that only contains the odd terms of the polynomial. So the even guy has x to the power 0, x to the power 2, x to the power 4, etc. And the odd guy only has x to the power 1x to the power 3, x to the power 5, but we'll divide it by x. In the normal definition, f even and f odd would have some gaps, but we're going to fill those gaps up. We're going to compress those gaps artificially. I'll show an example, and it will make a bit more sense than it probably does now. Okay, and the reason we come up with the polynomial next is because the polynomial next is exactly a partial evaluation of the initial multivariable polynomial. When we substitute the first variable by the coordinate where we want to evaluate. And then all we have to do is we have to check that f even is actually what f even should be, and f odd is what f odd should be. This is a simple exercise to see that what the slide says. What the slide says agrees with what the previous slide was supposed to say. All right, so we do it. I'm sorry, it says logarithm of the number of variables. We do it without the logarithm, just number of variable times. We come up with number of variables, KZG commitments, and then we never touch any multivariate polynomial ever, and we manage to commit to an evaluation of a multivariate polynomial. And like I already mentioned, in case we have several multivariable polynomials, we can also do that. Do that for all of them simultaneously, provided that we want to evaluate them at the same point. Okay, let's look at an example so that those that square root dynamic makes a bit more sense for us. So let's do an example with two variables. We started with a bilinear polynomial that looks like this. And then we substituted with a single variate polynomial of degree 3. So the terms that are multiplied by v0 are the first one and the last one, and the terms that are multiplied by v1 are the second one, and again the last one. Now, if we compute v even and v odd should only contain a naught naught and a 1 naught, and v odd should compute a 0 1 and a 1 1. So this line should make sense. Okay, I guess this line should make sense. I guess this line is the opposite of what the previous slide said. And then when we look at this line here, it's clear that what is left to do to get the actual evaluation that we're interested in is to replace x squared with v1, and there's really not a problem to replace x. Well, we don't really need to compute the square root of v1 or anything like that to do that. We're just, because there's really not any odd powers of x at this point. All the odd powers have been absorbed by the f odd. Okay, is this all of my slides? I think this is all of my slides. So let me maybe stop sharing for a second, and let me maybe show you some code. Okay, so this is what the code looks like. This is the chip in question, and this is pretty much all it has to do. So it has to do some evaluations of a single variable polynomial for the checks of the odd and the even half. It has to commit polynomials. It has to well, do the verification of the KZG at the very end. And then it does the folding part. And then the full cycle kind of does it all. Where's the full cycle? There is the full cycle. Okay. Yeah, so the full cycle. The full cycle does the folding, then it commits to the polynomials, and then it adds everything to the transcript. And then, well, I guess the interesting step is the folding, and the folding. The folding happens several times, and at each point it does the one step, where the one step is what was described on the slide, and what should be implemented in the code here. I'm not sure I'm able to run any tests right now because I don't remember where they are, but I guess that's it for me for now.
Yeah, I can.
Amit, are you still there?
Yeah, I can start sharing.
Do you want me to say anything else?
No, that was great.
Thank you.
Yes, so wait, let me see if I can go back. Yeah, so Yulia talked about the Gemini chip, and this chip is going to be used for the snark verifier. So Hyperplonk, what it does, it batches multiple queries to a polynomial into a single query, and that was what Yulia was trying to show, that how you can have these multiple polynomials output a single polynomial at the end. So after that, we need to verify that polynomial commitment. So we have to verify KGZ commitment from the Gemini. And what we can do to make this process more efficient is that right now the Halo 2 backend uses Axiom's Halo 2 backend uses the KGZ pairing check. So what they do is that for the snark verifier, they pair and batch all the KGZ checks from the Halo 2 backend and put it on EVM to verify, and the EVM does the verification. So they don't verify this KGZ pairing in the chip. So that's where we got the idea from E that we can take this KGZ commitment or this verification of KGZ commitment and do an RLC with the Halo 2 backend pairing checks, and then we can defer it to EVM. So the EVM takes care of all the KGZ checks in our circuit. So this work was done by Jörn, and I think he's at the Hacker House right now. So, and yeah, Jörn has really a great understanding of the code base. Yeah, he did that in a very short amount of time. So you can ask any questions about how the code base is working and how these multiple pieces fit into one. So what we want to do is that we want to build Protostar in the ecosystem and not suck like Microsoft, which is a Web2 company. So, and the next steps will be to implement CycleFold. And so what CycleFold would do is that we don't need to run the aggregation circuit. So once we have CycleFold, we just outsource this non-native curve operations to the curve, and then again fold the instance back into our single running instance. So instead of aggregating two running instance, we will have a single running instance, and it will be much more efficient. So by efficient, we mean we won't have to verify this Gemini. We won't have to verify these non-native operations in circuit for the verifier. So even after a CycleFold, we would have to do some non-native field operations to deal with these commitments. And Yulia had another project where where she found out that you can replace these non-native operations with a lookup, and with lookup it will obviously be much more faster. So we can also look into that, and there are some opportunities to to make the MSMs much more faster. So there is this library from MRATSIM, and he has one of the fastest libraries for MSM for the Grumpkin curve and also the pasta curve. So I can go ahead and show a bit of the code. So let me start sharing. So these are the non-native operations that I was talking about. So, and these are done with the Axioms library. So most of these operations are the basic operations like power of some field element, square of some field element, inner product. But again, this is a non-native operation. So this is inner product on the base field, and we use this proper CRT event to deal with the non-native field elements, because to do non-native field elements, we would have to decompose them into limbs and then make sure that these are taken care of, so there is no underflow or overflow. And then we have the secondary curve operations, which are these native curve operations, and these are done using this ECC chip from Axiom. And we do like scalar scalar multiplication, fixed base MSM, and variable base MSM. And these are one of the most expensive parts of the circuit. So the Protostar accumulator instance, it is a struct, and it has all these fields, which is instance, witness commitments, challenge, u, which is this parameter in a relaxed expression of in the relaxed expression, and then we have the error terms, which are both in the commitments and also as a sum. And as you can see, all these are represented by a vector of field element. And then we have this compressed verifier that I was talking about. So fold uncompressed is this function which does without compressing the verifier. And then the folding with compression is the one which is done to make Protostar, which is done to make the verifier much more efficient. See. So are there any questions up until now? Yeah, I forgot to.
Okay, can you hear me?
Yeah, I can hear you.
Yeah, a great work. And so my question is that you mentioned that you the current implementation uses Hyperplonk and the Halo 2, right?
So yes, so the backend is Hyperplonk. Halo 2, we are using Halo 2 as a front end to just write the circuit.
Okay.
Yes,
Okay.
backend is full
yeah,
Hyperplonk.
Halo 2 is just the circuit part, the front end of writing circuit, right?
Yes, exactly. Yeah.
Yes, I have another question about the Gemini. So there's another paper named Zero Morph, right? I remember that we're not quite sure that Zero Morph is another technique to transfer the multivariate polynomials into the univariate polynomial. So literally, it can also using KZ programming commands to commit the multivariate polynomials, but I'm not sure if any differences between them.
So yeah, I don't know. Yeah, maybe Yulia can answer, but on top of my head, I think there are multiple schemes to go from multivariate to univariate. Like you can use multilinear IPA, Gemini. You can use Gemini, Zeromorph, and there are some others. But yeah, the aggregation circuit. So in the aggregation circuit, we have to run one non-pairing based proof and then the pairing based proof. So that's why we need to make sure that they are compatible. But yeah, I don't know, Julia, have you looked at Zeromorph?
No. I have a strong suspicion that most choices are like about equally efficient. I think all different choices are more or less equivalent in this sense.
Yes.
Yes, I think.
Yeah, I have
ahead.
another. Yes, here. Okay. In Germany, we have to because in for us to encode the MLE, actually we use the evaluation form for the multivariate polynomials, right? I mean evaluation forms, but if we want to use Gemini, we have to do transfer the evaluation form of the multivariate polynomials into the coefficient form, right? Am I right? Something like equivalent to FFT in univariate polynomial.
You are, but well, since the points are plus or minus one, I don't think that's necessarily well, a super difficult FFT to do. But
Yeah,
yes, you are right.
Yes, I think there's a paper written, it's an informal document written by Habuk recently. In that document, he proposed an approach which is we don't have to do FFT stuff. We can directly use directly using the evaluation form of multivariate polynomials and into KZG10. Probably, I'm not that sure. It's just so that's probably, I think they are different, but currently I need more time to dive into it. Maybe you can discuss offline about that.
Thank you. That sounds
Yeah,
relevant.
sure. Yeah, I think so even with CycleFold, we will still have to, I think, use maybe Gemini for the final proofs. And if we see that maybe Zeromorph performs better, then yeah, we can switch it up. But yeah, let's see. Yeah, I think for us the two main points right now is to implement CycleFold and then complete this Gemini chip. So these are the two most important directions right now.
Yes. Okay, there was another discussion back in the August in Hackhouse in Suzhou in our lab. So I discussed with somebody so at that moment we went through the CycleFold paper, and in CycleFold paper they claim that actually all non-native failed operations can be delegated to the secondary curve. But actually, after that discussion, we found that okay, there are still